guess we can get started. Cool. Thank you guys for coming here. Today is our pleasure. It's my pleasure introducing our speaker, Professor Veronica Santos. She's a professor from UCLA. She received bachelor degree from UC Berkeley, and then she moved to Cornell for the master degree and also a PhD degree. And then she did her postdoc at South California, University of South California. That's one famous work from her group, work on tactile sensors. If you work on grasping, robotics grasping manipulation, tactile sensing, most likely you know that, biotech. Yeah, and then Professor Santos moved to the Arizona State for assistant professor a few years, and then to UCLA until now. Her work on tactile sensing, robotic manipulation, biomechanics, human-machine systems. Today, yeah, it's our pleasure to have Professor Santos here. And yeah, without further ado, the floor is yours. And thank you here again. And yeah, the floor is yours.
All right, thank you. I'm hearing a little bit of echo from my computer that I don't know how to turn off, because if I turn off the audio, I think we lose the audio and the video. So if there's no complaints on Zoom, I'll keep going. But thank you so much to you and everyone. I think it's fun. Yeah. Thank you so much for having me. I haven't been to Purdue since 2016, so it's fun to come back and see everything that's different and meet new people. I'm here to talk about touch today. I direct the biomechatronics lab at UCLA, and we strive to improve quality of life and quality of work by enhancing the functionality of artificial hands in human-machine systems. So we do that by studying how humans grasp and manipulate objects, how are they using their eyes in concert with their hands. We design tactile sensors and tactile perception algorithms, and then we use sensorized robot embodiments to develop new capabilities for robots. So you may have seen some of these older videos showing very dexterous looking hands. And I would argue that these state-of-the-art hands can mimic many complex movements of the human hand. But what is movement without touch? And so throughout this talk, I actually have a few videos that highlight some of the work done by a collaborator, Dustin Tyler at Case Western Reserve University, because I think it kind of hits on key points that I want to make throughout the talk. So we're going to start with this one.
Science correspondent Miles O'Brien had much of his left arm amputated last year after an accident while on a reporting trip for the NewsHour. He is
all right. Which one? It's already on.
since been exploring leaps forward for modern prosthetics. Science correspondent Miles O'Brien had much of his left arm amputated last year after an accident while on a reporting trip for the NewsHour. He has since been exploring leaps forward for modern prosthetics.
And feel free to adjust it as needed, okay?
A hand without a sense of touch isn't really a hand at all. It's more like a pair of pliers. Watch blindfolded hand amputee Igor Spedek try to pick up some blocks using a prosthetic without a sense of touch. It's not very productive.
That was no sensation.
No sensation.
And so you were just
going blind.
Just
literally going blind.
Yeah.
Now watch what happens when the sensory perception is turned on. It's like night and day.
But then when I grab it, if I grab it just right, I feel all three fingers. If I grab it right, or two fingers. Then I know I have it, and then I'll move over and drop it.
Is it your phantom hand that you're feeling it in, or is...
Oh, it don't feel phantom to me when I grab a block. To me,
hand.
it does not. It feels like my hand. It feels like something between my two fingers that's vibrating.
For Igor, who lost his hand in an industrial accident 4 years ago, something powered by a battery and made of plastic, metal, and silicon can become his hand.
Things that are the ways that we think about touch, and the very first one is that touch is useful. So whether you have robots that are working inside the body, intimately attached to the human body as with neuroprosthetics, working near the body for assisted robotics or cobot manufacturing, or purposely put very far away from the human body for extreme environments where you want to keep humans out of harm's way. We believe that when you are asking a robot to physically manipulate their world, that touch is an important complementary sensing vision. And just think about the many cases where vision is degraded, limited, entirely absent, even, putting on your bike helmet, you do not have a direct line of sight, but you're using your sense of touch, your proprioception, which is your understanding of where your body parts are and the amount of effort that you're putting in for all these things. And even the hand itself can occlude the object if you're working with something small. Maybe you're working in the dark, behind obstacles. If you have your phone in your pocket and the alarm goes off, most of us can reach into our pocket, find the button and turn it off without having to have a direct line of sight. And then you start thinking about more extreme cases in smoke, in turbid water. You're going to have times when vision is degraded and you need a complementary sense to help to make actionable decisions. And then I like to throw in some of these deformable types of objects. Back in the 80s, we were thinking a lot about very rigid objects. We have perfect models of them. But what happens now that we're starting to think about robots that are manipulating deformable things that have infinite states, and we may or may not be able to model them thoroughly in real time. So you have deformable linear objects like rope or deformable sheets. You have deformable bulk objects. Maybe these objects are also animate. And I was talking to you this morning. She gave me a good idea to add to this. What if they're animate and slippery? What if you're trying to handle a live fish or something like that? And of course, in-hand manipulation is a grand challenge that remains for artificial hands. The second point is that touch is multifaceted. So it is multimodal. I once had a reviewer send back a paper and they said, your paper on tactile sensing is not multimodal because you didn't use vision. And that was kind of the old way of thinking. Now, you can, you'll see like the Meta Digit 360 that is out now, and it has 18 different types of tactile features. So touch is multimodal, it's multifaceted. And if you think about the classic way that you learn about biological mechanoreceptors in the human hand, on average 2,000 of these mechanoreceptors in each fingertip, you can classify them according to where they are in the skin. They can be superficial, they could be deep. And then within those two layers, you have FA or fast adapting types of mechanoreceptors that responds to transients and very fast vibrations, things that are on off very quickly. But you also have slow adapting mechanoreceptors that respond when you have a long sustained stretch or something like that. And all this together enables us to have this elegant, beautiful sense of touch that I don't think we necessarily need to mimic for robots, but it is a really nice, elegant proof of concept of something that exists in nature to do all of these dexterous things. So we are somewhat agnostic when it comes to tactile sensors. We will buy them when we can, and when we can't find what we want, we start building them. I don't think there's any particular type of tactile sensor that works for every application. I think we like to start from the application and then think about, okay, what are the constraints? What are the size constraints? What types of environments to your budget? So we started with some low-cost approaches using piezo-resistive fabric sensors, and we were making puffs and things like that. We also took a page from Rob Howe and Matej Carly's work and embedded barometric pressure sensors like the ones in your cell phones in sensorized objects, because we were doing some haptic search experiments. We wanted to vary objects and also to track the forces that people were applying to the objects without putting the force sensors on gloves, because we wanted to retain the human sense of touch. We have also had more than a decade's worth of collaboration with Jonathan Posner, who's at University of Washington, making microfluidic tactile sensing skins. Our very first one was capacitive based, and where it looks like, those silver lines, those are actually liquid metal that are passing over one another. And where they pass over one another, they create a single taxel, which is like the tactile analog to a pixel. So imagine a bunch of little capacitors, which are great for sensing normal forces. But of course, the forces that we deal with in real life are three-dimensional. So a little bit later, we switched over to an entirely resistive-based approach. And you can think of these as liquid metal strain gauges. So I'm sure you've put lots of strain gauges on pieces of aluminum and done experiments in the lab that way. It's the same thing, but with liquid metal. And if you put them into these serpentine formats, then you can have directional strain gauges, and we use that to back out shear forces. And then if you use a spiral, you can now get isometric normal force sensing. And then by switching from capacitive to resistive, we found that we actually could sense vibrations up to 800 hertz. So we were able to make a skin that was multimodal and that it could do normal force, shear force, as well as vibration. We then took that sensor and worked to marinize it. And this is a project where the funding has since run out, but what we ended with was a tactile sensor skin that had the microfluidic taxels in it that we could test submerged underwater, and we tested it under various hydrostatic pressures to simulate depth. And I would love to get this work going again. But all the rage now, and anyone who knows Yushi's work and others, all the rage now is putting cameras inside fingertips, because you can leverage all of the computer vision algorithms for optical flow and things like that by now looking out at the world from the inside of a fingertip. And Ted Adelson came up with the gel sight. So we've collaborated with him and gotten a couple different versions in our lab. But the idea is that inside the fingertip, you have a camera, and it's looking at the inside of a deformable finger pad that may or may not have different types of coatings. You could have different colored LEDs, and by tracking the optical flow and looking at changes, especially at the micro scale, you can back out local geometry. So this is one of the gel sites being pressed against cables that were lying on top of sand. And by tracking the optical flow, you can rebuild force vector fields and infer what is being contacted. So more recently, we took the open source version of this. This is a couple of years old now, but Meta and GelSite collaborated to post online a recipe for the digit. This is not their latest digit. The latest digit is hemispherical. It's the digit 360. It's got 18 different features. It can even, can sense chemicals and through airflow. This one is basically an acrylic plastic. You have an elastomeric finger pad. You have a camera that is sitting on the printed circuit board at the back, and it's all one tight unit. And since then, I had a bunch of undergrads working on it. They got so good at it, they started to realize that they wanted certain additional features. So we've also added different types of markings on the inside, been doing our own custom lighting, swapping out cameras to have a wider field of view. And we've adapted it to a number of grippers in our lab. But the sensor you're going to see the most of in this talk is called the BioTac. This was something I worked on when I was a postdoc with Jerry Loeb. It was funded originally by the DARPA Revolutionizing Prosthetics Program. So it was designed to be bio-inspired and to go directly onto prosthetic hands, which is why it's human-shaped and human-sized. And it has a rigid core like the bone in your finger, an elastomeric skin that's inflated away from the core by a conductive fluid. And then if you tap into that fluid volume and hide a pressure sensor in the core, then you can sample that pressure sensor slowly to get an overall impression of gross force on the fingertip, or up to 2200 hertz, and you can pick up transients, vibrations. There's a nice paper by some colleagues using it to identify hundreds of different textures with this tactile sensor. There's also on the elastomeric skin, there are fingerprints. And the fingerprints are actually intended to amplify the vibrations as it's rubbing across surfaces. There's also a thermistor built into the fingertip, and it uses the rate of heat conduction away from the finger to infer material properties. But what we make the most use of is this array of electrodes that's on the core. So as the skin gets compressed towards the core, the impedance in this array of electrodes will increase, and you can measure the impedance of each electrode independently. And as the skin bulges away from the core, that impedance will drop. And so by tracking the impedance across the whole core, we can kind of infer what is happening to the shape of the finger pad locally. All right, so I've just shown you a bunch of different ways that you can collect information about touch. Aside from, electrical contact or sensing temperature, most of what we need to measure touch has to be deformable, which is why all the sensors I showed you had some deformable component. But that's just going to give you a stream of voltages or resistances or whatever you're collecting. We still need to abstract those numbers to something that has meaning, something that is actionable. So we think a lot about the tactile perception algorithms, which is why touch is abstraction. And some of our earliest work is inspired by this seminal paper by Liederman and Klasky from 1987, which is about exploratory procedures. So what they did was they brought people in and they asked the participants to report on different types of properties like texture, hardness, weight, and then they observed what the participants did with their hands. So if I ask you all, tell me about like the seat that you're sitting in, right? How rough is it or whatever? What would you guys do with fingers? You would rub it across, which is something that we've learned from just growing up, that if you want to get information about texture, you stroke your finger across the surface. So that's what they were observing, and they published this paper about the stereotypical exploratory procedures or exploratory movements that humans use when they want to extract certain types of information. If you want to know something's hard, you press against it, right? If you want to know about local shape, you would try and follow the contour with a fingertip. So that's the very first thing that we did. We took sensorized robot embodiments with that BioTac sensor, and then we had the robot do a bunch of exploratory procedures. And our earlier work was looking at edge orientation, bumps, and pits of different shapes and sizes. And you can see in these videos, it's just performing a bunch of exploratory procedures. And the key is to know what the action was, measure the results, the consequences, the perceptual consequences of that action, and then to bridge the two, and you're basically doing a calibration. So at the time, we were using support vector regression, SVR, support vector classification, SVC. So you'll see these stamps every now and then describing the types of techniques we were using at the time. But you can see as the finger is moving, these traces in this inset is showing you what the electrodes are experiencing. So if you see the impedance increase, that means over that portion of the finger, the skin was getting compressed. Then we moved on to tactile perception of directionality. And this is really about sensing what's going on to an object that you're already holding. So if you're holding an object and you want to set it down without looking, right, think about the reaction forces pushing against the object and how that will necessarily change the shape of your finger pad. It's going to shear your skin in a certain way. And so what we did was we took a robot, and instead of perturbing the object within the hand, we just flipped the model for data collection purposes, and we perturb the fingers relative to the object. And during these movements, you can actually see that green finger pad deforming, and we can collect information about that finger pad throughout this entire movement. So we collect a bunch of tactile training data, and then we think of them as images. So this was like the first time, the field had already been using, I think in computer vision, they've been using convolutional neural networks, but not so much in tactile sensing. And we thought, well, isn't the tactile image that we're getting just like an image? So we imagined that, you take off the skin of the core, you have an array of electrodes, and we just imaginarily rolled it out onto this flat surface. So you have your pixels on the XY axes. The Z axis is actually the change in electrode impedance. So if you see it increase, that means the finger pad is getting compressed there. And then that tells you about, this is like a height map that we can then turn into a grayscale image. Now we have images that we can match to all of these different angles. Yes.
So would you mind ask a question now or later on?
Yeah, go
It's
for it.
okay. Yeah. So for example, the BioTac here, when you convert the the signal to the image, how is the kind of X and Y or the density, the resolution for this image? It's like a 10.
Yeah, so that's interesting. We faked the resolution because we only had 19 electrodes, but they were all bathed in the same continuous conductive fluid. So we just assumed that we could interpolate, and we made our own manifold. Yep. Now, how much you can push that, I don't know. You obviously can't push it to infinite resolution. All right, so after we've now trained, we use machine learning all the time because the tactile sensors that we use are highly deformable. No analytical models exist, except especially for the biotech. You can model the mechanics of how the skin would deform, but not necessarily how the electrical current will pass through the fluidic volume. So we kind of threw up our hands and decided, okay, let's go the hardware data collection route. And by doing the pattern recognition, we were able to implement real-time reactions based on what the robot was sensing. So what you're going to see in the upper left-hand corner is this 360-degree pie and the real-time belief of the robot of the direction that the grasped object is being perturbed. And so I'll show, here's a simulated object handover where we're purposely not releasing the object until the robot senses a pull of the object away from the palm. And the second example is, setting down a glass and assuming you had perfect knowledge of the glass and the table, you might be able to do this really delicately, but most of the time you don't. And if you use the sense of touch, you can then decide when is the right moment to release the object that you're holding. One of the most fun things that we've done is to take tactile sensors and put it into granular media. So typically tactile sensor work is done in open air environments where it's very easy to tell when you're contacting something and when you're not. Now, if you plunge your fingertips into a granular media like sand or snow, now you are stimulating everything all around the finger. So then the question becomes, how do you extract information about the thing you care about while it's stuck amidst all this distracting noise? And so that's how we first thought about granular media, was that it was just this source of extra noise. But it turns out that if you take a tactile sensor and you put it in granular media, you can actually turn it into a proximity sensor. So through granular media jamming, we can do that. And if you're not familiar with granular media jamming, just think about all these particles that might flow over one another depending on the size of the particles, the friction characteristics, the shapes, and all that. You imagine you're at the beach or you have freshly fallen snow and you run your fingers through it. Some of those particles are going to get out of the way. But if you are moving towards an object that is immovable because it's buried, there are going to be some particles that get stuck because they're going to hit the object that's buried. And what happens is they create this force chain of particles, that will reach from the buried object all the way to your finger. And now you can sense contact at the finger, even though you're not directly contacting the object. So that's what I mean about proximity sensing. You're sensing something through the tactile sensor, but you are far away from direct contact with the object you care about. So in this video, in the upper right-hand corner, you have torque at the base of the finger. This is an estimated biotech force. This is, generally speaking, the force on the finger. And then my students created this video where the particles that are shifting from frame to frame are highlighted in white. And what you're going to see is anything that is moving from frame to frame, you'll see white, and you'll see this kind of area that's called the failure zone ahead of the finger. And all of these particles moving, now they're going to hit the object, and you're going to see an increase in the fingertip force, even without the finger touching directly the object, which is very useful if you're trying to use a robot to find something that is buried and dangerous. You may not want to directly contact it, but you may need to use touch to kind of localize where it is. And once you know generally where it is, the shape, then you can begin to think about the next step, excavation, retrieval, things like that. And so one of our earlier papers on this work was leveraging a very simple granular media jamming model. And here you can see our simulated failure wedge shown in green, and it's just moving freely through the sand until it hits an object, and now you're going to get jamming and you can start feeling something on the fingertip. So we used that same model on this robot. This is shown at 2x speed, but imagine one exploratory procedure, one movement, and this is just a simple linear movement, and now you can build an occupancy map. So this is the belief map of where something might be buried. And then you use that map to determine what your next exploratory movement or procedure should be to reduce the uncertainty in that map. And then you as the experimenter can decide what is your acceptable level of uncertainty and keep exploring haptically until you achieve that threshold. And so this is showing within 7 exploratory movements, which are chosen in sequence to further reduce the uncertainty in this map. And then this is showing on the bottom the truth after we. So I would also like to get back to this work. And you'll notice a theme where I would love to get more into field robotics and put tactile sensors in extreme environments like underwater and in sand, because I think not a lot of people are thinking about it, which is fun, and it's, you know, get to do some field work. But touch is very expensive. So anyone who works with hardware will appreciate that things break and it costs student time, and you know, your robot parts wear out. And so because we don't have good analytical models of our tactile sensors, pretty much everyone in the lab has to do hardware-based experiments. Touch is expensive financially and in terms of time. So it's important to think about resource-conscious ways of enabling robots to learn how to do tasks that would be hard or difficult to hard code into the programming. So we started thinking about reinforcement learning. This was our first efforts in that area. And we thought, okay, what's an interesting challenge? And we thought about something that is transparent, deformable, occluded by the fingertips, and we came up with closing a Ziploc bag. Right, so if you wanted to use just computer vision, it would be very difficult to track all these things. If you thought, okay, with computer vision, I can say the zipper moves, you know, from right to left or is at a certain angle, I'll just have the robot do the same thing. That video was just to demonstrate that that doesn't always work, because the zipper, if you don't adjust your movements of the fingertips, the zipper will fall out of the fingertips. So what we did was we set up this camera, and the policy that was learned only relies on touch, but we use the camera system to automate the annotation and the learning. But once you learn the policy, you can turn the camera off and use touch just to do this task. And we thought, okay, let's think of some very simple states and rewards. We really wanted to move the fingertips relative to the zipper. And so we decided, okay, we're gonna give 1 point for every time that the robot, you know, at the time step can keep the zipper in the sweet spot of the finger pad. If it gets too low or too high, we're going to lose the zipper. So, or the Ziploc bag. So that was how we set up states and rewards. And then you also have to pick your actions. And this kind of asymmetric set of actions was, we came upon that after doing some preliminary studies, but now we have our state, action, and reward spaces. And what you need to learn first through exploration is, what is the relationship between my action and my state, right? If I do this type of action, what is the resultant state? And then that determines whether you get a reward or not. And if you have explored enough possibilities and you feel like you have a good understanding of the state, action, reward space, that's when you now exploit the policy that you've been learning. But there's always this constant tension between exploration and exploitation, because if you only exploit, you may not be able to handle new novel situations, which is why you want to sprinkle in a little bit of exploration every now and then. So this is showing some of the training that we were doing. In the upper left-hand corner, you're going to see the impedance values from the BioTac sensor. And then on the lower left, you're going to just see some annotations about what the robot thinks is happening. But this is doing some exploration. And the goal is to really get from the starting location all the way to the end of the bag, because that means you actually close the bag. So you can see down here in the lower left, that deep neural network classifier is saying, okay, low center, oh, center, so it gets a +1, right? And it's gonna learn by doing. And at some point, when we feel that we've learned the policy sufficiently, then we can try that on novel situations. This particular paper was a comparison of Q learning and contextual multi-armed bandits. And the way to think about multi-armed bandits is, well, does anyone know gambling and what multi-armed bandits is a nickname for? Yes.
Consequência a non-sequential information. Like it means like it's not an MD.
I actually meant not mathematically, but like
Okay.
if you walk into a casino, what are the one-armed bandits that are there?
Wow.
Slot machines. Okay, so the analogy is you've walked into a casino, you only have so much money, you have precious resources. I only can run my robot so long before a student needs to graduate or the robot's gonna break. So where do I spend my money? Well, exploration of that slot machine space is trying out the different slot machines, finding out which ones are paying out well. And then once you've learned kind of that state action reward space, now you can really exploit with the rest of your resources. So that's what this paper was about. And once you've learned the policy, now you can test it on these novel situations. So most people here probably know McMaster car bags, very stiff. So we train on the stiff bag. And then for the testing, we swapped in these more flexible kitchen bags. We put different types of weights in it. We also tried to extend this to cables, but it did not work very well. We also tried teaching a robot how to flip a notebook page. I know a lot of these examples seem contrived, but these were really proofs of concepts of how to bring tactile sensing into a reinforcement learning framework because they're not used that often. Most reinforcement frameworks are based on vision and not touch. And so in this example, to simplify things and make the problem tractable, we took this robot arm and constrained its movements to the plane. We gave it a binder that we had put motion capture markers on, and then we had two fingers, a top and a bottom finger, and the goal was for the robot to learn what it feels like to turn the page successfully and the right way, and I'll show you what the right way means. One of the things that I find so ironic about reinforcement learning work these days is that it's always used to teach a robot how to do something, but no one ever talks about all the reinforcement learning that the student did to get the robot to do that. Because you can't just craft a reward function effectively if you don't yourself as the experimenter know what's important. And so I've seen students spend months trying to figure out what's important in my data, what are the important patterns so that they can craft a reward function. So I don't think that, we talk about reinforcement learning with robots, but I think it happens with the human first. So my student put together this reward function based on his intuition of working with this robot and staring at lots of tactile sensor data. That includes the fluid pressure from that hydrophone inside the BioTac, the impedance, so some description of how the finger pad is changing shape, and then we put in a penalty for excessive binder movement. You don't want to really drag around the binder while you're doing this. And then we had to come up with kind of the good and the bad cases. And so the ideal case would be the semicircular trajectory. So imagine you have a binder, and from the binder rings out to the width of the page is some radius. If you know that radius in advance, you can do this ideal trajectory. So just move your robot with that same radius about the binder rings. But if your movement radius is too small, then you're going to crunch the paper and you get this page warping and snapping that I'll show you in a second. If the radius you choose for robot movement is too large, now you're dragging the binder around. So I think the middle one is the most interesting one to watch. But you can see all three cases. But the middle one is going to show you, there's going to be some warping here. And then that part right there was the snapping. And we can actually pick that up with the BioTac. You'll see a little spike in the hydrophone data. So I'm not going to belabor the plots down here, but there are 3 points I want to make. One is that the top finger shown in this row experiences something different from the bottom finger. Within the finger itself, the different electrodes experience something different. So the different parts of the finger pad have different experiences. And then within each finger and each electrode, we see repeatable and differentiable signatures for each of the three behaviors. That is the most important part for learning. It has to be repeatable and it has to be distinguishable. Otherwise, you can't learn the pattern. And so this is what took a long time to figure out, and eventually that led to the successful reward function. So after we learned that reward function, we wanted to see, could we adapt a nominally learned trajectory to a different context. And in this case, the context was, learning on a small page and then suddenly surprising the robot with a large page and vice versa. So this is showing how we can take that nominal trajectory that we've learned and then over a few policy updates using touch only, adapt to a new context. All right, so now I'm going to switch over to some of the things that we have been working on more recently. We are still doing some reinforcement learning work, but not ready for prime time just yet. Don't want to scoop my students. So I'm going to show you some of the things that we've been working on in the meantime with teleoperation. So everything I showed you so far was really about developing semi-autonomous behaviors for robots, not really with the human in the loop. But you can share touch. So I'm going to revisit this segment from Dustin Tyler's lab so you can get an idea.
Brandon Presswood lost his arm in a workplace accident in 2012 and is also a participant in Tyler's study. He too had surgery connecting his nerves to sensors in the fingertips of a sophisticated prosthetic limb.
Basically, they've mapped where if they put this electrical signal to this contact on the nerve cuff, then that makes me feel a pinprick in my index finger.
But he doesn't even have to wear it to get that feeling.
The fact it's attached to his arm is actually kind of arbitrary. We can put the prosthesis anywhere in the world, and he would still feel like his hand.
Presswood is trying out the idea with his prosthetic arm mounted across Tyler's lab.
And so now we can extend his capability. We can essentially amplify the person by taking that sense of connection, the sense of touch, and putting it on any machine in any part of the world and bring it back to your nervous system. And then I can connect it to devices that can do far more than my weak biologic system.
So that's what we embarked upon right in the thick of the pandemic. It was 2020. And, Dustin Tyler founded the Human Fusion Institute at Case Western Reserve University. We had UCLA, Cleveland State, University of Colorado Boulder, and University of Wyoming. And we all threw our hat into the Avatar X Prize. But basically, we want to directly connect the human and the robot experiences using what Dustin calls neuroreality to enable humans to be physically in one place, but experientially in another. And I know that teleoperation, telepresence, this is not a new idea, but we're coming at it kind of with more state-of-the-art technology these days and joining everyone else who's been doing this for a long time. And our long-term goal is not just to enable humans to use robots as remote tools, but the dream would be to enable embodiment. Just like you would want a robot that's intimately attached to you, like your prosthetic arm, we would love for, through the sense of touch, to enable people to feel like that robot is not a tool attached to their body. It is their arm again. It is their hand again. And that is, those are some of the anecdotal things that Dustin has been hearing through his experiments with individuals with limb loss. With the touch sensation turned off, the prosthesis is a tool. With the touch sensation turned on, it is my hand. And that's what we would love to do, but at a full body, with mobility and grasp manipulation capabilities, that would be the dream. So this is the Avatar X Prize system that we put together. It started with an operator system at Case Western Reserve University using the Oculus Quest and a glove with electrotactile displays I'll describe in a minute. And then in our lab, we were the robot system experts, and we purposely chose a system that we wanted to make use of beyond the X Prize. So we weren't necessarily trying to win the X Prize. We wanted something that was safe, lightweight, portable, small footprint, things like that, which is why we went the minimalistic route as opposed to 5 robot arms and things like that actually won the X Prize. And for this system, we focused on 2 key things. Stereoscopic vision, so enable people to look around on their own, and then enable people to feel. And anything in between, right? We didn't think it needed to be anthropomorphic. It doesn't have to look like a human body because when I'm talking to you, I'm not really caring about what the rest of my body is doing. I'm looking around, I'm gesturing. And so we focused on vision and touch. And then we had super cheap force resistive sensors that were built into this particular Tasca prosthetic hand, but then we also had an undergrad team add some more because we wanted more contact locations. And then we used those force sensitive resistors to proportionally stimulate this electrotactile haptic feedback play. So as you saw, Dustin Tyler's lab is well known for using peripheral nerve stimulation, but that's an implanted approach. So we were thinking, okay, how can we make this system and experience available through wearables? And that's what Dustin's team has been working on. So that early work on the X Prize has led to our current work, which is funded by the Office of Naval Research. We've spent the past year just building the system. We're getting excited to actually do some interesting experiments with it, but system integration for anyone who does hardware here, you realize that it is non-trivial. There are a lot of parts. We have components coming from multiple universities. It's taken a long time to get to this system. And for various reasons, we ended up with an asymmetric bimanual system, but it actually has worked out pretty well. So what you're seeing on the right is the Meta Quest headset. We purposely put a joystick for now for simplicity in the non-dominant left hand of the operator here. What's not shown in this particular photo is the electrotactile ring system, but all of these parts will have counterparts on the robotic system. So the dominant arm, which is the Franca Amica arm, has 7 degrees of freedom. It has a leap hand on the end, which is weak, but has multiple digits and can be moved really fast. And then on the non-dominant arm here, the left arm, we have the UR5E. So it's only 6 degrees of freedom, but it's used for fixturing. It's not used for doing the dexterous manipulation work. It also has a 3-digit adaptive robotique gripper, which is not necessarily dexterous, but it is strong. So we have fixturing capabilities on the non-dominant arm. We can do manipulation on the dominant with the dominant arm, and then both grippers have the actually customized digit tactile sensors that I showed you earlier. So each of these fingers has sensors that can be used to proportionally drive rings. Now the ring system shown on the upper right is the current research-based version, but Dustin Tyler's team spun out a company called Afference, and they just debuted this ring at the Consumer Electronics Show this year. So we are looking forward to trying out these rings. Again, the approach was portable and mechanically transparent, because there are some applications where the operator does not want to wear a glove. So that's why, if we can make rings that people can still type with, they can still pick up objects and manipulate objects without having a glove degrade their natural sensation, that's what we're going for. So I've got a series of 3 videos kind of showing you how we've been using the system. The first one is on the physical calibration of this neurohaptics display system. So in this video, the researcher on the right will first put the rings on the participant's finger and help to adjust the electrode placement. So there's a pair of electrodes at the base of the finger. And then once the placement of the electrodes is done, then the user themselves can turn a dial to pick a range of stimulation that is comfortable for them. And the goal of this is really to make your haptic display system have the widest range possible while still being comfortable. Because the wider the range, the finer the mapping we can do from the tactile sensors on the remote robot to perception on the. And then we have in virtual reality a set of training tasks. Not shown in this video is an additional calibration where subjects can now adjust, if they want, the ranges on all of their rings at the same time. And then once they feel like they have it where they want it, then they can do tasks like testing the stiffness of virtual avocados and sorting them. And once they get used to what that feels like, then we start testing them on a simulated version of the real robot. So this is a reaching task just to get people used to moving their arms to get the robot arms to move. And now this one is actually reaching around some obstacles. So the red spiky things are things you're not supposed to touch and you have to reach around them to grab objects. And then on top of that, we add an additional requirement that they don't just touch the object, but they grasp it at a certain level of force for a certain amount of time. And in order to achieve that, they need touch. So they're using the haptic feedback to do that. And then we do that through the joystick for the non-dominant. This is just kind of a free play stacking task that enables them to try out the different movements that they have tested under more constrained situations. This one's kind of a fun one because with virtual reality, you can degrade the visual feedback. So imagine this kind of dappled shower door where you can kind of see, but it's definitely degraded. And the non-dominant arm is going to place a block behind that screen, and then the dominant arm needs to grasp it. And when vision is degraded or even entirely absent, you really have to rely on the sense of touch to know if you're making contact and if you've got contact on both, say, the index finger and the thumb. And then what you could do by knowing the robot kinematics is you can kind of give the operator X-ray vision. Like if it's completely opaque, but you know the kinematics of the robot arm, then you can project something for the operator so that they have a general sense of where to haptically explore. Then they can use their sense of touch to confirm and grab the object. Once they've done all this in VR, we can now bring them over to the real hardware system. And so in this task, we have some objects that visually look similar, but have very different stiffnesses. And so the operator has to rely on the real-time tactile feedback. And we've heard anecdotally that participants are using a combination of the tactile feedback intensity along with their known grip aperture, because we don't have any proprioceptive feedback for the operator. They have to know what they're doing with their own hand, but in combination with their known grip aperture and what they're feeling through the rings, they can infer stiffness, they can infer size. They've even commented that they can use the rate of change of the tactile feedback to infer things like stiffness. We haven't tried to push the limits on speed of movement. For the tasks that we care about and the audience that we care about, they move slowly anyways, because we want to move carefully and thoughtfully around high consequence devices or materials. Next one, the very last point is that touch is connection. So pretty much everything I've thought about my entire career and even all the videos up until that point was very task oriented. How do we use a robot to either perform a task on behalf of a human or support a human to perform a task? It was all about function. It wasn't really about anything social. And I think that, affective computing has been around for a while, but, it's been a pretty small community. And I think that a lot more people are going to be thinking about the way that touch plays a role in social connections between people. During the pandemic, our labs were visited by Cynthia Gorney, who wrote up an article on a number of labs around the world, just describing the importance of touch. Not from a functional perspective necessarily, but there's a reason why a newborn baby, why it's so important to place that newborn baby on the chest of the mother to have that direct skin-to-skin contact right after birth. So touch is more than just performing a task. And so I would like to finish with this last video that gets to that point. Full of students here who may be thinking about, okay, what am I going to do for my PhD? Or now that I'm graduating, what am I going to study next? And I thought I would end with a slide of kind of things that I think are things I would like to see developed. I feel like they are gaps in our community's knowledge and very important for all of the things that I've talked about today. So these are some exciting directions that I think are kind of untapped. The first is combining proximity and tactile sensors. I talked about using a tactile sensor in granular media and turning into a proximity sensor, but there are people doing some pretty cool work by adding proximity sensing directly into fingertips. I've also seen some work along the lines of putting cameras inside arms, like forearms, and then having the forearm itself be electrically opaque or transparent. So if it's transparent, your camera can be used for proximity sensing. As soon as it gets opaque, now you can use the deformations of the forearm as a tactile sensor. So that's what I mean about interesting ways of combining proximity and touch. Sim to real, we don't really have good analytical models of tactile sensors. We have a lot of data that we can use of real hardware and mapping that from the action to the perceptual consequences, but that is expensive. So if only we had a tactile sensor model, which in some cases, if you have a bulk material like this with elastomer and a pattern of particles inside, you can create a simulation of that and how that would deform. But things like simulating how the light refracts and things like that, how current passes through fluidic multimodal sensors, that is very difficult. But if we had these models, you could train a lot of policies in simulation before testing them on your robot. And I saw earlier today some students presenting about the importance of testing your controllers for quadrupedal robots, before you do that on the hardware, because it can be very expensive. Robots for social physical interaction. This is a new subfield that I'm seeing emerging. So human-robot interaction is when you have humans and robots in the same system. And social human-robot interaction, you can think of like robots that are designed for autism, right? They might sit there and they're moving around and they're socially interacting, but there's no contact. And then you have physical human-robot interaction, which is like some examples I've seen in literature would be like, I need to move this table, I hold this end of the table, the robot holds the other end, and we are physically coordinating our movements together. Now you have social physical interaction, human-robot interaction, which is like robots for high-fiving, robots for hugging, robots for handshaking. And it is an untapped area because of this power of touch. And so if you haven't read about the HuggyBot, there's some really nice articles out there by Dr. Alexis Block. She was a postdoc in my lab, but she was collecting data on cortisol and things like that, showing that hugs can reduce stress. And it's not just a matter of making contact. There's all these different parameters. What is the proper appropriate length of a hug? Where on the body should you hug? How hard should you hug? All these things that bring in the social aspects of touch. And I think that's an exciting area. And then finally, if we are going to develop these robots that eventually can enable something more like embodiment as opposed to a remote tool, that can enable marginalized populations to be included in societal activities again. Kids who have immune system problems and they need to stay home, they can't go to school. I have a colleague who sends robot avatars into school on their behalf. Robots that in Japan, you can go to this cafe where individuals with impairments are logging in from home and they are controlling these waiters that serve you. So I think these are some interesting areas to think about. One thing I didn't show is large area tactile sensing. If you noticed, everything I showed you is really on fingertips. I would love to go from fingertips to palms, but that's still not whole body. And if you start scaling up tactile sensing to whole body, you're going to need to collect your data and process the data in a more intelligent way than we're currently doing, which is why I like a lot of the event-based neuromorphic type of things that I'm seeing in the computer vision field. It would be great to see that in the tactile sensing area as well. So none of this work would be possible for me to show without the amazing students, collaborators, and funding agencies. So I'd like to thank them and thank you for your attention.
Fantastic. This is a wonderful talk and very inspiring. Thank you so much for sharing us the exciting work and also promising directions for the future for PhD students here. So now, we can open for questions. Yes.
Yep. Can you speak up a little bit? Sorry.
When human touch something,
yes.
Human cannot feel or not only just force, and then temperature? Do you think temperature can be another source of?
Yes, yes. So some people are thinking about temperature from a tactile sensing, but also a haptic display type of method. If you want robots to be interacting with people, probably don't want them to be cold. So touch is very important to sense. The only downside of touch is the time constant. So you have to touch the object for a certain amount of time before you can infer the material properties or the temperature. But it is an important modality of touch. Yeah. Also, the like the lubricity, right? When you touch something that is wet, it's also that sensation. Yes.
Yeah, thank you very much for your platform talk. So actually, I am a student, so we've been working on self-robotic link with the proximity and tactile sensing with the skin that can change the transparency.
Oh, awesome.
Thank you very much for you mentioned that. So actually, I have been also working on large area tactile sensing during my PhD. So do you think, so what would be a good application that we can leverage the large area?
Yeah, so for assistive robotics, where you now have robots that are assisting with dressing, getting in close proximity to individuals who may be impaired or aging in place, knowing where the contact is happening just makes the whole system safer. So imagine you have, some strong robot arms that are coming in to help someone put their jacket on, but they can only feel on fingertips. They have no idea if they're pinching or hurting some part of the body if you don't have another way to sense, beyond torques at joints, sensing other contact with the environment, with the human. So I think that's why I think that large area tactile sensing is so important, and it really hasn't been tackled yet.
So you said touch is expensive, right? So because the sensors you wear quite quickly. In your lab, do you have issues when if you had tried to do the simulation? Let's say the sensor was not the limitation there, but collision or like between solving collisions between soft body to soft body and getting the force properly.
Yeah, I know that you can infer contact forces by assuming, rigid object, rigid support surface, and the inner penetration distance. But I don't know, it never seems quite good enough. I guess you can get normal contact forces that way, but we wanted even more richer information, so we didn't even really bother with that.
You're showing the computer vision, like machine learning map models being able to create that grayscale image. So like, is it?
Well, we created the image, but we used computer vision algorithms to do the machine learning pattern recognition.
So the image is composed like impedance sense, right? So, but do you also have like the time sensitive data about like trying to feel if something is like a bump?
Yes.
So, and then follow-up question, then like when I'm also like feeling a bump, I also know like how my finger is oriented to. So do you have like time orientation? Yes.
So when we were doing the bump work, that was our earliest work. So we were still doing support vector classification and regression. Then we started doing convolutional neural networks. But in order to do the granular media jamming perception, we started using recurrent neural networks because we weren't using any of the time-based information before that.
So you had to combine like almost 3 different types of data at the same time.
For the bumps and pits, we didn't. If I were to go back and do it again, I would definitely use the time information. Yeah. It was more about looking at the full trajectory and classifying those, or at least classifying snapshots of them. But I think if you think that something dynamic is happening and that dynamic information is being encoded by your sensor and is important, then you got to do something with the recurrent neural network to collect that, to capture that temporal information.
Gotcha. I think we got some questions from online.
Oh, okay.
Patrick, are you there? Maybe you can unmute yourself and ask a question.
Yeah. Hi. This was a beautiful talk. Thank you so much. I'm glad I was able to watch it. Can you hear me?
Maybe you can type the question.
Yes, maybe I can ask a question on behalf of Patrick. Can you type out the question? The first question is, so the talk is fantastic. Thank you so much. Patrick has 3 questions. The first one is, what is the force resolution of the fingertip sensor?
It depends on the sensor. We were initially trying to get like 0.1 newtons because the literature suggests that when humans are haptically exploring, they use a very light touch, but it's very application dependent. So if you're trying to grasp a pipe underwater, probably don't care about 0.1 newtons, and you have a very large range of, so there's a trade-off. There are sensors that can do like sub-Newton, like millinewton type of sensing, but again, I think it depends on the application. And what we really care about is whether the tactile sensor encodes information that is important to make an action, like is actionable. Does it encode the information that helps me to make a decision? And if so, then I only need that bare minimum of information.
That makes sense. The second question is, what is the sensing bandwidth? I guess you just mentioned the 0.1 hertz for some applications.
Yeah, it depends. Again, like the resistive microfluidic tactile sensor skin, that particular one with the strain gauges, we went up to, I think, 800 hertz.
I see.
But it depends on the type of sensor because it's another reason why we like the mechanically transparent haptic devices, because you don't have as much inertia to deal with. It can be like instantaneous that you send information directly into the nerve.
The last question is, are the materials soft so that we can penetrate with some sharp objects?
Oh yeah.
Thinking about whiskers.
Oh yeah. Again, depends on the application, but most of them are soft because we use them in the lab and we can afford to make new finger pads when they wear out. But I guess one thing you could put on the exciting new directions would be skin that self-repairs. I've seen some papers that have skin that self-repairs, like they'll make skin with like pockets of elastomer or liquid or something where if it gets sliced or punctured, it'll fill in and heal itself. But that is one major problem with artificial skin, is it's not like our biological skin where it heals over time. Yeah, so robustness is a big problem. We can show a lot of things working nicely in a structured environment in the lab, but you try and put them underwater, you try and put them, on a robot foot that's running around on sand, and it'll just get destroyed. So robustness is, if you care about things outside the lab, robustness is a big challenge.
Yeah, I hope these answers.
Yeah, it's a trade-off between you want something that is soft because then you can pick up all that deformation, but if it's too soft, it's not robust. And if you start making your skin too hard, it won't deform and then you lose sensitivity. So there's a sensitivity robustness trade-off. No question?
Sensing the data is converted into an image, right, for the fingertips. And how would that differ when it's happening all over? And how difficult would that be?
It would be very difficult because that's just a lot of data, especially at high resolution, which is why I think event-based neuromorphic approaches would be more appropriate because, then you only care about the sensation when it's important to care about it. Right? Like you're sitting in your chair, but you're not necessarily thinking about how your back is contacting the back of the chair, right? But if you were sitting there and a fly landed on your arm, you would feel that and you pay attention to it. So it's kind of about the resources for processing, attending to something. So I definitely think if we're going to scale up, we need more clever ways of processing and dealing with the data. Okay, how in the front?
Yeah, so for the inspired tactile sensor, I see that you use two kinds of data source. One is the array of the electric signals, and another source is water pressure. So why is this water pressure necessary for this kind of sensing? So does it provide a more bandwidth and the electrode provide a better resolution?
Yeah, if I recall correctly, I think the electrodes are sampled at 100 hertz, but you can actually sample the hydrophone up to 2200 hertz. So you can get transients and a lot of vibration data. There was another hand in the back on the far right corner.
I'm curious about your opinion on the large area of tactile sensing.
Oh yeah.
Because I think that will involve a lot of information because the area is large and also you can have temperature, force, a lot of information, and also if the robot is in different configuration, it could also contain spatial, like even time dependency. So it sounds like a really complicated problem. How would you like define the?
So the question is about large area tactile sensing and how you even go about it. And I would say if you're going to use the traditional approach of like every Tactile has a wire connected to it, that's probably not feasible. The closest thing I've seen to large area tactile sensing, I don't know if it was actually done, but Chris Atkinson at CMU, he was a consultant on Big Hero 6, so he was really into Baymax, wanted to build his own Baymax. And at the same time, there were people working on, I don't know if it was his group or another group, but they were putting cameras behind membranes. And so his idea was to put a bunch of cameras inside Baymax that looks out at the world. I think that's one of the advantages of cameras is that with one frame, you get so much spatial information. You don't get the temporal information when you're limited by 30 frames per second, 60 frames per second. But in one snapshot, you get a lot of information, which you could like look at an entire inside of a forearm or a belly or a back without having wires going to every single Tactile. I think that would be pretty messy. Another question?
I have a general question that might not be with the official, but what's your opinion on using touch sensors, the robots enabled with touch sensing for collaborative work, when multiple robots use an object. And then do you think the current state of the art in the sensing is sufficient enough for doing that, or do you think that something what you're doing would be helpful for?
So your question, the application you're thinking about is robots that are collaborating with one another? What type of collaboration? Through an object?
Yeah.
Yeah, I mean, you could do that just with a force sensor at the wrist. A lot of robots don't even have hands. So I think it depends on the level of richness that you need about the touch data. Are tactile sensors done in terms of design? No, I think, like proximity, tactile sensing, high bandwidth, plus resolution, there isn't any one tactile sensor that can do all of these.
We have another question from Patrick from online. Maybe we can try to use my computer and see.
Okay.
Yeah, Patrick, could you try to speak, like, unmute yourself?
Yeah. Can you hear us?
Yes, now we can hear you.
Yeah. Thank you so much for giving this talk. I have so many questions, but I think because the granular media, I think that the Dan Goldman, that kind of model approach. Yeah. So I was wondering, have you thought of like putting this on the sole of the foot? So basically, at the end of the day, use this as a feedback to jump on a sand.
Well, for a long time, I've been trying to collaborate with someone who does legged robots, and I've always been told your sensors need to be more robust because within however many gait cycles, they're just going to be destroyed. So I think most people who do legged robots, will use kind of binary contact sensing approaches. And of course, you can't put like a $6,000 load cell on the end of each foot. That's too expensive too, and they'll get broken for sure. So yeah, I would love to. There's a nice complementarity between locomotion and manipulation. If you've never seen this video of like someone, actually, well, you can see videos of humans holding spheres and kind of juggling them, right? So that's the manipulation part. And there's also videos of like dung beetles that are they're using their legs and they're rolling around spheres of dung, but you can also flip that model because now the dung beetle without that can locomote. So there's some interesting parallels between them. They're not identical, but you can think of things like gait cycles for walking and also gait cycles for manipulation.
I feel manipulation is much harder than locomotion.
Well, yeah, I envy also what people do with locomotion because I feel like a lot of what we do with manipulation is slow. And with locomotion, especially bipedal, you don't have a wide base of support. You have to be able to think and react very quickly. So we haven't really been doing things at speed. So I think there's some envy on both sides.
Yeah.
Question here.
So the proximity sensor application, for instance, we showed the granular media. I believe that materials behave differently in the dynamic situation. So your loading rate, if you move fast versus slow, it makes difference. What do you think about the loading rate dependent behavior of the sensor?
For proximity, in granular media?
Can be running or any.
Okay, yeah, loading rate plays a very big role, and that was something that was just beyond the scope of that particular paper. But the depth, the force, the compaction of the soil makes a difference. Between each trial of that granular media, we had to kind of reset the bed because we'd already compacted the granular media, and you have to reset it in order to have a nice new trial. So yes. Force rate also makes a difference. But depth is something we played around a little bit, but I think that needs to be further explored, as well as different types of motions. We were only doing something linear, and we kept it at the same depth. But that's not like scooping, and that's not like contour following, which are more advanced.
You see progress being made in dexterity, but can robots achieve human level dexterity and fine motor skills?
I don't want to anger anyone who sells commercially available artificial hands. There are some that look very human-like and they can have very human-like motion. So if that's what you're after, being able to recreate the kinematics of the human hand, I would say maybe roughly with a lot of money, you can do that. Actually controlling a hand as dexterously as a human, I think, is not just about the kinematics, but it's about the sensation. So the tactile sensation, but also the proprioception, knowing your pose and the amount of effort, and then doing all that very fast. We don't have robots that can do hard tricks that I know of yet. I have seen robots that can do juggling of balls, but you won't see that capability when you turn the hand over. You see the robots that are doing the Rubik's Cube with one hand, but you can't turn the hand over because you're relying on the palm to support. So you're not thinking about having to maintain grasp at the same time as doing the manipulation. So I would say there are very impressive demos. And for people who think about touch, we're always thinking, okay, how can I break that? And one easy way to break a lot of these demos is to have to turn the hand over, right? A lot of things, demos I also haven't seen are ones where you're using some fingers for stabilization and other fingers for manipulation. I haven't seen that too much either. Yes.
Yeah, I have a question about perhaps using tactile activation in addition to tactile sensing for teleoperation.
What do you mean by tactile activation?
I don't know if this is the right word. Maybe
the haptic display?
Yeah, haptic display may be a better word. So getting the human to feel what the robot feels at the remote site. So for instance, there could be large area context that would involve large area activation.
Yes. Yeah, so there are people who are working on, like Heather Culbertson at USC, she was working with Alison Okamura, and the two of them were working on sleeves that use pneumatics. And if you have the spacing just right and the waveforms just right, it can feel like a stroking motion. So that has its own difficulties as well. So you think about like the wires that you would need for all these individual taxels in a large area. Now imagine trying to put actuators that need power and need to deform and are wearable. That's a whole nother challenge.
Yeah, I guess integrating tactile sensing with haptics display.
Oh, yes. I have a student who wants to do that. Oh, yeah. I have a student who's working on that. I haven't seen that too much. A single wearable that can do both the tactile sensing and the display. One of my students wants to do that.
Great. Yeah, thank you all for engaging discussions, and our speaker will still be here for at least 10 minutes, 15 minutes. If you have other questions, feel free stay here and engage and have more discussion. And thank our speaker again, and yeah, thank you all.
Thank you.